So welcome to the second lecture, I guess, about attractor dynamics. This is we call it historically we call this subsymbolic. It's using attractor dynamics now in the spirit of behavior-based robotics. I introduced that initially. So I first make that little contrast. So what I lectured last week, we had these different contributions to the dynamics, and they were associated with objects. A target was an object, different obstacles were objects. And we call that symbolic in the sense you have to instantiate instances of these. If you have a perceptual system, you would have to, I list that here, you would have to detect this environment, assign maybe a number to them, extract the parameters, the estimates of the position, distance, and so on of the obstacles, and then erect the contributions to these that they make to the dynamics. In fact, in cases where this is done, there's often also dynamical processing, for instance, Kalman filtering, where you're using current sensor information, but combine it with previous estimates. And that's where you see that. You have to say, is this a new object? So do I need to start a new Kalman filter, or is this just an update of a previous object? And there's a whole technology of how to do that. And for this particular problem, obstacle avoidance, this is actually not necessary. And I'm showing this as sort of a exemplary case study in that, and contrasting these two kinds of approaches. So this goes beyond just using the attractor dynamics approach. This is a general problem in using autonomous robotics, using sensor information. You can either have high demands on perception, leading to objects, categorical percepts that you then track over time and process on. And that is the sense world acting, or you do this at a lower level. And this is what I'll illustrate today. And the vehicles lend themselves to do a lot of that, but a similar contrast exists also for robotic arms. So I'll take you through that. I will actually illustrate this in terms of obstacle avoidance, which really lends itself to that, because with targets, typically when you have perception information about targets, it is really a particular location or a particular object, and there you would then actually have some process of identifying it uniquely versus another one. And the example I showed where you just take the nearest target like location is not really typical. That's where you have task information. There's this little subtlety that I will get to when we talk about navigation, that targets in space, you think of targets characterized by landmarks, like I meet someone in front of the bakery store, let's say. But actually, it turns out that landmarks are sensory cues to a target that don't really require necessarily segmentation. No, segmentation means knowing what sensory information pertains to the object and what does not pertain to the object. And that's not always necessary. For instance, you can say, I'll be at the target if I have this view, if I have these colors around me, like this position, then I know I'm at the lecture table, for instance, right? And we'll get to that. So for now, in the discourse, we'll have target will be treated the same way as a categorical thing and a discrete thing, and then we'll see in the implementation that we actually use dead reckoning, have a real map for it, and so on. So the obstacles. Now, the obstacles are really just obstructions in the path, right? Something that you need to avoid. And in that respect, you don't really care if they're different objects, as long as you can't go through them. You could also say it's a question of free space representation. So between the obstacles, there is some space you can go through, and that's what you're interested in. And so I'll tell you this in the concrete sense, and then next lecture, I'll actually show other approaches that do it in slightly different ways. So in our sense, what we do is that we have sensors on board of the vehicle, these little red markers indicating sensors, and you'll see implementations later, that are distance sensors. In some cases, actually very crude kind of distance sensors. In the more ideal case, it will be a time of flight sensor like a LiDAR that gives you precise distance information. Our sensors actually are just some function of the distance. And so you would have a discrete number of these mounted on your vehicle, fixed, they're mounted screwed to the vehicle, so they don't vary where they look. And the notion would be that each marker erects a contribution to the dynamics. So a little repelling force of that nature that is erected in the direction in space. Remember, this is this coordinate frame in outer space, into which this sensor is currently pointing. So for instance, this sensor is currently pointing in this direction. That's this angle to the world axis. Now the vehicle is heading in this direction at the moment. And so you're right, this is the heading, right? And this is a particular value of the heading when it coincides with the direction in which the sensor is pointing. That's where the repulsion will be from. So that varies when the vehicle rotates, right? While the sensor is mounted, of course, at a fixed angle. We'll get into more detail later. Yeah, that just states what I already said. I will be using slides from an unpublished paper. So I put the link into the PDF, you can look that up. This is Estelle Bicho, who did her doctorate thesis with me when I was in Marseille, even though her degree is from a Portuguese university, and she now leads a group in Guimarães in Portugal, where she does a lot of this work. And I'll show some of her more recent work at the end of the lecture, just a brief hint. We wrote a review paper, but then for some reason we didn't really push through, so it never got published, unfortunately. She has a very nice preprint. So here, just make this idea a little bit more concrete. So here we actually have 7 sensors in this instance, and we'll go through this picture several times. Now we're just looking at one contribution, let's say, of this. I don't know which sensor it is. It doesn't say that. Just one of those sensors. And again, remember they have 3 parameters. One parameter is where the zero crossing is. That will be, again, this angle under which it is, pointing. Let's say it's the sensor here, the direction to which it is pointing from the world axis. The slope of this, which we will discuss in a moment, and the range, so some width function. It would be strictly speaking where this really goes to 0. And in these, the formulas are in that paper, and they are like the formula that you studied in the last exercise sheet. So they're really Gaussian, so that would go theoretically to infinity, and it's actually problematic because the angle is periodic, so it would be actually quite a mess. But in practice, when it's small enough, it's getting neglected. In previous work, we really cut it off and were very precise about that. Now, in this kind of work, it doesn't really matter because it's all very low-level noisy and so on. So the noise and the variation from time step to time step is larger than the position of this little tail there. So it's a good approximation. It's an exponential. So let's first look at, the equation you're familiar with. Those who looked at the exercise. And you see that the only variable that shows up in this equation is phi minus psi. It's the only form in which these variables show up. We'll see it shows up also in the sigmoid in a moment. And if you go back to the scene here, you see phi minus psi, I say like minus psi, minus psi plus phi. That's this angle here, right? That's a constant. That's how the sensor is screwed on, right? I can look that constant up, like 30 degrees, 60 degrees, or something like that. So in other words, here on the right-hand side, these are constants. So there isn't actually even any need for this purpose so far to really know phi, or psi for that matter, right? So that shows a little bit the charm of that, right? But of course, what we do need is we need to use sensor information in some way. What we use it for, we use it to say that only those sensors that sense a short distance should contribute. If they sense a large distance, then they should contribute less. And one particular way of doing that is to have an exponential decay, which again has the scale. We talked about time scale last week, and spatial scale is the same idea that you could sort of say over which distance does the strength decay by fixed factor, and that would be this beta that then determines that scale. So when you sense d, then the strength here, the slope of the linear function, would be modulated in this way. And the overall strength, there's a factor in front that modulates the overall strength of the obstacle avoidance term. So that's how sensory information enters actually into this. And then there is a second aspect: how wide should what should the range of that thing be? And here's an interesting little subtlety which really plays a role in practice. So you have two contributions to the range. One is the sensor range. So depending on your sensor, you might have a cone, which we call here this delta theta, that within which this sensor detects distance. This could be exact, like if you have a leader, you can actually find that. Or it can be approximate, so like we use in some examples infrared sensors, so they send out infrared light and then they detect the reflected light, and the amount of reflected light is a function of distance, and there is some sensory characteristic, like the beam we send out is somewhat limited. Actually, in practice, we just put a little rubber band that limits how the light is spread, very crude. See, that's not an exact sense of distance because it also depends on how much stuff is there in that cone. So it will reflect more if there is an object that is across the entire angle, and less if it's less, and it also will reflect more if that's a white surface than a black surface. So it's actually not very precise, but it's some function of distance. And so that would define the sensor cone. So certainly you would want to make the width at least as wide as that. But then there's a subtlety in that you would want to avoid, let's say the maximal object that could give rise to that sensory signal would be one that spans the entire delta phi, the entire sensor range, right? So to avoid it, you would have to make sure that when your vehicle is right there, it fits, right? And fits would mean that half the vehicle width, we model the vehicle as a circle, half the vehicle width on the left and half on the right would be appended. And that means that you have to expand that range by the angular width, right? It would be the angle under which you would see the vehicle if it was up there. And if you figure that out, it's the tangent of that. And so the correct way is to add the tangents. So this will be the tangent, add the tangents, take the arcus tangent to then have that angle. That's how that formula comes about. You can figure that out, that this is the correct range. This is assuming that it's under some approximation. So that has an interesting consequence, because it will mean that when you avoid the same obstacle at a closer distance than at a larger distance, this angle that you add is more, because the vehicle is larger in angle when your vehicle, if it is at the obstacle distance, extends a larger visual angle than if it's far, right? That's stuff that comes close, grows in size on your retina, let's say, it's your visual angle. So that would mean that you can figure that out, right? And you see this in the formula, the distance shows up here. So if the distance is small, this term becomes large. And so the consequence is that as you approach an obstacle, the forcelets become broader. And you will see that means sometimes that there is a bifurcation happening, that before you thought there was an opening, but as you get closer, you see it's broad and it switches to not having an opening. That's actually a cool feature of this approach. So that's how the individual forces are designed. So once you know this formula, here everything is specified. I listed the lambda here, right, and then the theta, and the distance, the sensor information shows up here and here. That's the only two places where something shows up, and you see that everything else is just constant, right? Even in this formula for sigma, these distances and so on, that's all constants. Right? So it's really very simple. That's why we were able. I'll show you at the end of the lecture an even more radical version, which we were able to implement on a very low-level robot, and it had only like 100 lines of code. And it's due to these kind of simplifications in there. And then 100 lines of code is more like reading the sensor and so, more infrastructure stuff. The math is one line of code where you write down that formula. It's also true at the action end, because at the action end, I'll explain the summing now, but at the action end, we have essentially the rate of change of heading, right? So it's just the turning rate. And that's what you need. You don't need to give the wheels a new desired orientation. You just give it a turning rate, which is the speed of the wheels, actually the difference in speed of the wheels with some factors, that depend on how large the wheels are and how large the vehicle is. These are velocity servers. You give them a turning rate, and that determines that's the phi dot versus phi. So you don't need to know what's on the right-hand side in detail, right? You just need that number. Good. So here's an example. So let's say this is actually was obtained from actual data from a vehicle that I'll show you later. So this is a case where only the sensors 6 and 5, I believe, sense something, an obstacle. Everything else sense nothing. And you calibrate this that there's a maximal distance that these sensors can sense. These infrared sensors don't look very far, actually, maybe like half a meter. And so after that, it's zero. So you make sure that the beta is such that by that time, the strength has really fallen off to be negligible. And so only the ones that send something closer to that will make a non-zero contribution. So here you see at the direction in space where 5 looks, sensor 5 and 6, they are repulsive forcelets that will then superpose. So we're just adding again the contributions, like for the symbolic approach, they superpose and then they make the repellent in the middle. So the middle will be in somewhat this direction, which happens to be very much the orthogonal direction here to that obstacle. We drew the obstacle in as a square. It was physically some box, and let us see these boxes that we did in the actual hardware. Now, if you rotate the system on the spot, it's still the same configuration where the vehicle is, but it's now pointing in a different direction. Now it's sensors 4, 3, and 2, or is it 3, 4, 5? I think 3, 4, 5, or maybe not. It's only sensor 3 and 4 that now sense the obstacle. And the plot looks very similar, except that it's now psi 5 and psi 6, but previously it was, sorry, no, it was still the same sensors, right? I'm confused. Well, should be 3 and 4. Maybe this is wrong here. I don't remember. We'll see in a moment. So what I'm going to ask now is, why does it work? Because I'm a bit worried. Why does it work? Because every sensor contributes that forcelet, right? And if the vehicle rotates, the forcelet rotates with the vehicle. And so, and that's not allowed, right? The dynamics is supposed to tell you for every heading direction what the forces are. If you go to another heading direction, that line here should tell you what the turning rate is. So if you just shift the function, it doesn't tell that. It would then be whatever the turning rate is in that shifted function. And this would be like the carrot and donkey, right? And the carrot makes an attractor, let's say, but then as the donkey moves to the carrot, the attractor shifts, right? And that wouldn't be kosher dynamics with a donkey. That might work actually because it has some mental stuff to actually represent that a little bit. I'm not sure it actually worked with a donkey, that it actually really does that. But some of you, the Germans, might know the Lukas and the Lokomotivführer. I don't know if you're maybe too young to know that. In my childhood, that was a book we read, and this guy invents a perpetuum mobile for his locomotive, where he has a magnet that he puts in front of the locomotive connected with a beam, and like you can somehow turn it on and off, and then this locomotive can fly, right? Because the magnet, when it's on, pulls the locomotive. We all know that doesn't work. It violates the law of conservation of energy, and it's that thing that the force is actually not really as one would assume naively, because it's not invariant under a change of the dynamical variable, and as you change the state of velocity, the force also changes. So the force isn't actually the force that really determines the future. So, so that could be a concern, right? And I'll illustrate that it's not a concern, and when it's a property, and that also shows that things have to be done right for this to work. So here is the first situation that I showed, and I'm just marking here in red where the current heading is. So if I'm now driving that vehicle, it will sense that. For instance, this is this heading here. Here it's, I think, critical that we get this right. So this is to the left of that. So smaller angle. So here it's correct, plotted correctly, right? So the phi increase to the right, and that is going to the left in the picture on the left, right? So the heading is here at smaller angles than the angles that point to the obstacle. This is in sensor 5 and 6 sense the obstacle, and this is where they sense where the repeller is, which is at pi half. That will be vertical. Huh? The horizontal axis is the 0 axis, so pi half would be vertical, and that's a very good estimate of where the obstacle lies in this direction. Right? That's where the repeller is. Now, if we rotate it on the spot to point here, now the sampling of the dynamics is here, a little bit larger angle than 90 degrees. So 90 is here, is a little bit to the right of that on this axis. And you see now it's actually 3 sensors that contribute 2, 3, and 4. These are the individual contributions. They're a little bit different because only the sensor that points right in this direction has the short distance and therefore steeper. And the other two have a little larger distance, this angular, this distance here, the diagonal one is a little larger, and therefore they have a smaller slope, and this shows up as a smaller amplitude here. And the 3 superposed to this black line, and the black line has the repeller still pretty much at 90, exactly in this direction. So what happens is that the black line, the sum of these terms, is pretty much invariant under rotation of the vehicle. And that means that this is a consistent dynamics that we're actually doing there, right? Even though the individual contributions move, the sum is correct, and that's because the world is invariant, and the sensor information, in a sense, reconstructs or estimates the angle in the world. So this is actually only approximately true. If you look into the details, it's not perfectly true. And so that's ultimately a question of how this is modeled. That is, if you do the sensor model right with the width and the distance dependence right, then you will get that invariance. And we did it just ad hoc and sort of tweaked the parameters until this was pretty good. And that's what you would generally have to succeed in doing. And so behavior-based robotics has to make this kind of analysis. If you don't use dynamical systems, the same problem arises. It's really just a question of how you mathematically formalize that. Now, I'll give you an example, a very primitive behavior-based approach that a lot of kids do when they program robots in this Lego system. What's it called? Mindstorm, I think, right? Mindstorm? It's a Lego kit. It's great fun. Later, I'll show you. We actually used that circuit. It was before Mindstorm. Mindstorm was a product, but it's the same chip. It's a board that the MIT then commercialized, and the programming language comes from that MIT kit. Now it's available. Now you're a little bit too old to play with Lego, I guess, but if you have kids in a few years, that is really fun. And there you can program a low-level robot, and it essentially has distance sensors like that. And what a lot of people do when they first think about it, right? They have a sensor like in the middle of the vehicle. And when there is, let's say they have 2 sensors, one to the right, one to the left. And then if they have a distance, they send something that's closer than a certain threshold, then they will say, if it's closer than the threshold on the right, then I should turn left. And if it's closer under the threshold on the left, I turn right. And it would be rare for the 2 values to be exactly the same. And so that is sort of a naive algorithmic analysis, but it's not clear what kind of dynamics that really is. And these vehicles will all end up in corners. They create attractors in corners. You can think through why that's the case. We actually participated this decades ago when we did this really low-level stuff in a competition where people programmed their robots, and they were not kids, so they had a little bit more sophistication, but it was very much algorithmic for most of them. And in the final demo day, almost all of these robots ended up in corners. And in fact, some of them created corners with each other, like they would block each other and make corners. You can maybe think through why that's the case. Can come back to that later. So this works because of that invariance properties. And I wanted to put up an exercise next week. Tomorrow or today, I'll put up an exercise that's still about last week. And I wanted to do one because it has some interesting pedagogical points, but I have to figure out if it's if it's doable. The exercise so far, in my view, were quite trivial, and we'll get a little more advanced now. Let's see. Good, that's why it works. Now, the target acquisition is just added on as yet another term. And again, we could have conflicts here. And this is the conflict situation we want to look at. We looked at that in the symbolic approach, right? When you have the target and it pushes you to the obstacles, that's when you're challenged. And if the obstacles are far enough, this is a case where only one sensor here on the right, I can't read the number, but somewhat theta 3, I think, and this is theta 5, only those get input. And this is from actual sensor readings here. The repeller is exactly in the target direction. So this direction here is exactly where now there is a repeller. So this has gone through the bifurcation. You can see why. If you put that vehicle left and right, the angular range of these would be such that it doesn't fit. And so you have to actually make sure parametrically in the design that this is not doesn't have an attractor in the middle. And in fact, I have a sequence here of situations, again, from actual readings that illustrate that bifurcation. So here I have a case where there are only two sensors, I think, that get input, and the opening is just right for it to pass through. So you see the two contributions here, number 2, number 6, as a thin line, somewhat smallish. I hope you can see that. And then the sum of just these two contributions, so just the optical sum, see, does have an attractor in the middle. It has a repeller here corresponding to sensor 2. So here's correct. On the right, that will be small angle. So here's the repeller for that. And here is a repeller for that one, right? Repeller 0 crossing with positive slope. And then between those, there's an attractor. This is the attractor that comes from being repelled from one side, and the other side now that leads to an emergent attractor. If you add the target attractor here in the total, the sum, you have a very nice attractor here in the middle, goes through. If you now move the boxes a bit closer to each other, then it actually engages 4 sensors. Here, the 4 sensory information, piece of information. Now you see they superpose enough to make a single repeller in the middle. And if you add the target, this is the target acquisition. So the target would want to make an attractor here, but the obstacles overpower that. And again, that's the slope that you engineer to be right, so that the target, the obstacle contribution has priority. And then you will see that the emergent attractor is somewhere in the back, pretty far back. And you will see when I show you the simulation, for these things to be right, we have to make these obstacles quite broad, and they are broad means broad range of over which the contribution is active. In the exercise last week, you checked that once you're outside the range, you are no longer influenced. But if you're still in the range, you're influenced. So if they're pretty broad contributions, then it's not enough to be parallel to the obstacle. You actually have to go a little bit back. And this is where the attractor is pretty much in the back. And you see the robot turns a bit too much, goes a little bit away. It's not so elegant, but that's the price of doing it at this low-level style. So here is a systematic scan of that. So Echtella at different distances, put these boxes at different distances, and then we saw one sample here on the left and one sample on the right, so where we have a repeller and then have 2 attractors. In some cases, these attractors are actually just a single attractor. See here, this is can sometimes be 2 attractors with a little, you can see if you just change things a little bit, you could go through this here and have 2 attractors, or it fuses into a single attractor, which means that this is the same as attractor set, and it's just periodically plotted here periodically as 2 different numbers, but it will be the same number. I actually think that this is the case here. Is it? No, yeah, it is, because this is like minus pi half. This is pi 0 pi. So this is 90 degrees, or by half, minus by half. And this is a little less than pi half, and this is 3 pi half. Yeah, so 3 pi half, let me check. No, this is actually not true. These are still separate, but then they could become, under some conditions, they could fuse. Good. So that is how you design these, you have a lot of constraints to design this, right? And design really just means here adjusting the parameters. You could also think of that as choosing the functional form to make this right. In the past, in this first paper, we cite somewhere, Dose Schöner, we actually really designed the functional form and proved mathematically it's all exact and so on. But later we saw that it just is one can do this much more crudely, and that still works and makes it more easy, simpler to implement. Good. Here's implementation of that. So this is the vehicle that we built in Marseille. You see someone walking around. That's the engineer Pierre Mallet who built that vehicle. The vehicle has a computer on board. It's about 40 by 40 by 40. It has two motors. So two servo motors that are very good. They were very expensive. I was in Marseille Director de Recherche with a budget of about 5,000 euro a year. So it was really very much on the cheap that we built that. And these servo motors were the expensive things Swiss made. Everything else was extremely cheap. There's a computer screen on the back so that we can monitor what's going on. And there's a keyboard that later we had an infrared keyboard with a connection, so we didn't have to put it down on the device. The keyboard wasn't actually isn't included in the estimate of the radius of the vehicle, so it would sometimes collide with a keyboard, right? That's just how amateurish that is. This was the time when this was still all challenge. It's like in the late 90s, right? It's just ancient time, probably before some of you were born, or a lot of you perhaps. And to the computer, this is a PC, a complete PC. It was called an embedded PC. It was designed like a cube like this, and that would run the things. Once we ran DOS because we didn't want minimal overhead, and you can't put a hard disk on a computer like that because of the disruptions. Now, of course, you all have solid state memory, but at the time that was very expensive and rare. We did have solid state memory, but it was like minimal and very expensive and real hassle on the computer end. Like the operating system that can speak to that memory couldn't speak to other parts. So there's enormous progress in robotics, even just on this trivial side of embedded computing and so on. Right? That these days, like you don't even realize how on what you're sitting on, how much comfort you're sitting. So anyway, that's just the story. So the sensors are here. Actually, you see these little black buttons here. Those are ultrasound sensors, which we used for some other project. And on top of that black button, there's a little knob, a little hard to see. I have a picture, I think, somewhere later. And that's the infrared sensor. It's an emitter and receptor. We also had microphones that we used for something else, like for the target being a sound source and all kinds of other things we did with that. But here I'm just showing the obstacle volumes. So for this demo, the robot actually knows where the target is. It's somewhere here. It knows it in the sense that it knows its initial position and orientation. We assumed that. And then it keeps integrating its motor commands to estimate its position, path integration, which is, of course, not very precise. So after some time, it will accumulate error, but for these short-term things, it works. I'll show you later a wheelchair that we did this way, where this actually really works in practice. So it knows that its target is, that's why it stops there somewhere. And the only thing it does is obstacle avoidance. So in this series, we're actually opening the opening here little by little. You see it turns away more than it needs to, and it doesn't have a global plan, right? It doesn't know that it would be better to go around this way. This is Pierre Mallet who kind of shortens the excursion by blocking the way. So this approach deals with dynamic obstacles, moving obstacles very naturally, as long as they move slowly enough for the system to reach the attractor and stay in the attractor all the time. And so this would be like empirically demonstrating that it does the bifurcation right. Of course, we did the bifurcation empirically by turning off the forward speed, as it would be turning on the spot to figure that out. Right, the forward speed is this is a universal problem that they tend to oscillate a little bit in here. pretty much all behavior-based approaches have that. It's really when you're turning a little bit, then you're losing the sensory information on that side, and then it will turn back, and that's this kind of problem. Good. So this is the data from that kind of situation. I don't want to go through all of those. So the one interesting aspect is that you have as you approach the obstacle, you will go through that bifurcation as well. So for instance, here, initially, the obstacle forces are 0 because this is too large. It's about one vehicle size that these sensors can look. So they don't sense anything. As it approaches, starts to sense something, and it has already a repeller here in the middle, I guess, right? Is it? That's where it's looking. Yeah, already has a repeller. And then but it's still overpowered by the attraction to the target because of the large distance is a small slope, right? Only as it gets closer does it actually have a strong repeller here. So the different line types are the different sensors. Here's just one sensor that senses the obstacle. On the exercise sheet, I will be asking you, is it this week or next week? I'll ask you whether you're going to think about it, what the front sensor does. And it's kind of surprising. And I had to convince one of my students empirically because they didn't believe it, but it is true. So this is the front sensor, and it doesn't actually do anything. Well, I gave you the answer, but think about it. So here it's 3 sensors that contribute, and they create these forces. So there's a stronger repeller. And now I think there is a real repeller here. So it starts to move away, and you see that the path, it's just turning now as it go around. And so then it will go to the target. This is when we vary the opening. So the bifurcation we just looked at, and again, it's approaching. So first has a clear attractor. Now it's 2 sensors that sense, but there's still an attractor, and it gets closer. The steepness of the contributions is enough to make a repeller here, and then there's here this attractor to go around it. And then even larger opening, the attractor, and even though they make a repeller contribution, the width situation is such that the attractor remains. So it has an attractor all the way through. And you see here the problem with this oscillation is that some sensors might not actually sense sometimes to the left, and so it has to wiggle a little bit to see that. And this is just an illustration that as it moves around, then of course heading changes quite a bit, and the different contributions change quite a bit. As you see now, it's different sensors that sense that, and so the attractor, so the curved path means different heading, that the attractor was at different headings at different moments in time, right? So the attractor moves, and the system has to track the attractor. This is just the same. And here's an illustration of that. So this is along one of those paths. These are 3 different paths, and I don't remember which is which one. Maybe it's the 3 in the sequence I showed. Doesn't really matter. So it's in time tracking the actual heading direction. That's the black line on the robot. And then these different symbols are attractors. So we can record from this computer the dynamics it had and compute where the 0 crossings are with negative slope, and therefore we can compute the attractors numerically off the sensor data. We only need to know the position for the relative to the target, and then these 7 or was it 9 sensor numbers, and it will then uniquely determine the dynamics. And so you see here it has a single attractor. The target, I think, initially heading here toward the target, so the target will end up at that direction. And then this is where the bifurcation occurs as it approaches the wall. And you see it's a pitchfork. There's a repeller here in the middle. It's a very nice pitchfork, very symmetric. Now it's heading right to that, and the left sensor and right sensor are pretty much at the same angular distance. And see, it's actually not exactly true because it looks almost like there is a little opening here, right? That could mean that it's actually maybe more of a tangent bifurcation of these two, and then a new repeller comes in. But roughly it's a bit short. And and as it drives around, these again will fuse at the back, and then they don't really matter. The obstacle contribution doesn't really matter anymore. Now, what you see is that it takes a little time for the system to switch. So it gets initially stuck on that repeller in the middle. The repeller has a very small turning rate, and so it takes a little while to turn away from the repeller. And you actually need some noise to get away from the repeller. There's ample noise here in the sensor data, in wiggling, and also just the sensor itself is very noisy. So that alone would lead to noise. But we actually did implement in the algorithm also some noise. The computer it was written, I think, even in BASIC or something like that. And there was a random number generator in there. We actually added noise to make sure that, in a way, to make the escape deterministic, you need noise to make the escape time more reliable. If you rely on sensor noise, if you have a very quiet period with less noise, you take longer to escape the repeller. So that's this delay here, right? So this is one instance or one factor how this is a heuristic approach. It's not guaranteed to work because escaping from the repeller is a stochastic property. This would be a case where it went through when the opening was broad. So that illustrates how the dynamics actually change, and the system is always sitting in the attractor, except to see sometimes it can deviate for a moment, especially near bifurcations. So that's the theory of this low-level story. I'll show you now some demos, some stuff we did with this, and then I'll show you at the end of the lecture a next more radical approach that sort of illustrates, maybe that shows what the abstract principle behind attractor dynamics is. Any questions up to this point? I'll put it clear, but good. So here's literally this vehicle in just more interesting situations. This is, we use these white boxes because they reflect this infrared light very well. You could define very well the arrangement. Here is the target. This is always the starting position, so I'll go back. And so it finds that opening. See, it overturns a little bit, overturns again, and finds that target. So it does, we call that emergent wall following because you don't have any special thing about walls. And then here we started there, and the target is this. So it heads right for the target, as you see. And it gets deflected. I always try to turn to the target. That's why it goes around the corner, right? It always tries to turn to the target, but it's repelled by the wall. And that's how it goes around this wall. And then, again, tries to overturns here a little bit, and then tries to turn to the target. And that's how it actually finds its way into this open. Kind of, yeah. So that's also an interesting observation, and this is generally true about this behavior-based stuff, that it is low level, it doesn't have a world plan, it doesn't know about the map and anything, but it does behave surprisingly reasonable or rational emergently. And ultimately, this comes from the structure of the world. The world has pretty much continuous walls, with a few openings. It's not these random point-like obstacles that you have in a theoretical analysis where you prove exactness. You have to avoid any kind of configuration of obstacles, right? And imagine what that can mean. But the real world has obstacles of a certain size, continuity, and so on, and that actually enables behavior to emerge that is maybe not theoretically guaranteed. Here is an example. We close off this here. It heads initially in this direction because it goes to the target, and so it would points to the target. So it finds the other opening, right? That looks really intelligent, right? But it's just emergent from that sort of environment. Yeah, so that's the point. And this is why this is actually a doable approach in the real world. So we built a wheelchair. Pierre Mallet, who was this research engineer who built this thing. Actually, his daughter was in a wheelchair and had a neuro disease that made the joystick control difficult. You know, when you can use the joystick, everyone loves to use the joystick. But there's some people who have motor problems who can't do that or can only intermittently do that, but not in the continuous mode. And so for them, a little bit of autonomy would be good. It's an unsolved problem. There are huge research projects on that. And they're always about instrumentation, you know, like in your home, you have to build a map and all this kind of stuff. Very heavy, very expensive, never works. This was very, very low level. It still didn't make it into a product because of the economics of this. Because the number of people who are like that is very small and it can only cost as much. We had a grant to product and we ultimately failed. For instance, you have to pay 2 million euro to just get the license to put the controller onto the bus. These wheelchairs all have a bus like the car, CAN, CAN bus. It has a double form of that, duplex form. And there's one company that's called actually Dynamics in New Zealand that controls that in a way, the software. And to be a product in this so that you can enter this bus, you need to pay something up for this service or whatever it is. And this alone was too much for us. So it's an interesting story about how to create products in the medical sector. So we did a real test with patients in a place, you know, where they these kind of people are living and you know where people can move the wheelchair are pretty much sitting all day until somebody moves them, right? And so for them just to drive around a little bit was great fun, and they were all very enthusiastic. It's not really that they can go places with that, right? It's too limited, but they can move a little bit around in the hospital or in the living place. And so the notion here was that we had a lot of these low-level sensors. You can see that, but they're these small little things. We had to buy like 1,000. You couldn't buy them. Like one is a cent or something. You had to buy 1,000. So we built a little sensor by applying a lot of these sensors. We made them more powerful. They could sense larger distances because they were so cheap. And then we put the program on a laptop just for the demo, right? But you could build that on little platine with a standard digital processor. So it could be as a product really cheap. But again, there will be a small number, and then you need an interface for every patient, every participant, right? So here it was just a demo, but these people have usually some kind of interface, like they can intermittently, maybe with their head or their mouth, have a computer control. And so they could intermittently give a target, because the idea would be you give a target every now and then, and that target doesn't have to need a map. You can just say from where I'm now, I want to go 3 meters and a little bit to the right. So like on the computer screen, we had little a pattern, and you select one of 9 locations. And that's the direction it's heading. And the robot behaves reasonably because it just follows the wall. So if you want to go into a room, you point something on the right, and then it will go through that door. And if you don't want to go through that door, you choose a target ahead, and then you choose next target to go a little bit to the right and go through the door. And so that worked pretty well. For every patient, you would have to have that interface, and that makes it expensive, for instance. I have some videos here, and you know, it's not a circular robot, so there's some problems with that. You have to think about that. And it can really go through narrow openings. You have that little, I think I have that on the next slide. So here it just moves, and like here, there are a few examples where it turns in a relatively narrow situation. I don't remember exactly which one that is. This was in our laboratory building where we had, like from the 50s, it actually did have these somewhat narrow doors. See here, here's a maneuver. So we had to do some stuff to make that work. Yeah, it goes through a relatively narrow opening that way, turns quite abruptly this way, and so on. The speed is it's also an interesting issue. You know, the speed, because you don't want to. This is actually reasonable speed for an autonomous wheelchair. You don't want to go much faster than that. And the speed is determined. I mean, of course, this vehicle might have some speed, but other than that, it's determined by this logic that you have to be able to track the attractor. Right? And so you have to say, what is the fastest rate at which the attractor is going to shift. That will be always if it's sort of on the side. See the angular bearings when you move for objects that are on the side will be moving fastest, right? Something in front moves barely. Like if you look at the moon, it barely moves when you drive around. And then if something gets very close, right? So you can get an estimate from that, the closest kind of thing that you want to deal with, that your avoidance will ever generate, and if it's at 90 degrees, and then you can compute how fast it will move in an angle. This is to show the display and stuff. It's not so. It will move at an angular rate, right? And so then that's the speed at which I have to track the attractor. Now the time scale of the dynamics is an arbitrary thing, right? I have a relaxation time of the dynamics, and I could make the dynamics just fast enough to track that speed, right? So the limitation on that is the numerical integration of the differential equation. If the differential equation is as time scale is very fast, I have to solve it very, very fast. And that's the question if I can do that. In some of our experimental robots, the processor was so bad that the computation took so long that we couldn't compute very fast, very quick rate. But in practice, that's sort of just too cheap a computer. But in like this computer, the PC would be comfortably fast for that. In other cases, it is the sensors. Well, the sensors need some time to set up this infrared. There's the flight time, but that's negligible. But they need to average a little bit. It's like heat, It's infrared, and the sensor has some time it needs to make a measurement, and you have to do that separately for every sensor because they interfere. And that gives you the minimum time for one time step. We get one reading from every sensor. We even did things like doing at every cycle, we only did 3 of the sensors and then the other 3 for the next time step and so on. And then that limits the time scale of the numerical integration. And that's, if you go through, that determines how fast you can go. And so this is about how fast we can go. This is okay, because you don't want to go much faster with a patient on it. But so there's a real logic to that, right? You don't have to remember that, just to show you a little bit the style of thinking that is required in autonomous robotics. Very typical that you have hardware constraints, computational constraints, sensor constraints, right? And then there are environmental constraints. You don't want to move like a bullet through a hallway. Good. So this is a long time ago. This is more recent, and this is very interesting work that Stella and Wolfram Erhagen was another student of mine, and they actually met in Marseille and then married. They're a married couple in Portugal. He was from Bochum originally. So they have this team where they build team robots. So these are 2 robots that are essentially the robot that I showed you before, but much better in terms of hardware. And they are cooperating. And there's a very cool paper that you can look up where they this one avoids an obstacle, and keeps the load balance. It's really extraordinarily cool. So it's all really just what I taught you, but it has more forces. It has forces of one following the other, and it has some kind of virtual obstacles to avoid so that the configuration stays intact. And they have a thing to make sure that the obstacle, the thing it transports, doesn't collide with something. And it's all dynamic. Actually, this is Wolfram Erhagen, I believe. This is someone else, I don't know. Yeah, so this is sort of really the high art of that. And they did this is a demo for academic paper. They also have a project, or had a project with this German company, which I also forget if it's Bosch or Grundig, where they did that on the factory floor. It was still a demo, but it was taking this one step further with an industrial robotic platform and some other constraints on how to actually do that in practice. So this is cooperative robotics. There was a paper earlier by a group at Penn State, actually, UPenn in Philadelphia. I actually went there to teach that approach. It's always been my experience that you need to teach it because it's too abstract somehow. And they developed a swarm robotics approach. I mentioned that, I think, last time. A swarm robotics approach where many robots can coordinate and so on. And they did a demo, but it didn't transport anything. It was just them configuring, and then they could separate to avoid an obstacle, and then could reconfigure. It was more like a demo of principle. Okay, so that's the attractor approach in a low level way. And that's the approach that has been applied in many other contexts. I want to finish, no, this is just everything I explained here. Finish this lecture by showing you another approach, which we actually historically developed. We had actually, this is not quite right. So we published it before this work, but this work was just a follow-up on previous work. So it's about the same time, let's say. And this is, I'll show you, and then in the end you sort of will get the point. It's cool in a certain sense. It is, for instance, it's been used by a team who worked with us for a while on drones. Drones actually, autonomous drones, right? And you know, the drones that we're seeing in the war are not actually avoiding obstacles, to the contrary. But if you want to use drones in agriculture, for instance, then you want to do obstacle avoidance with drones. And this approach might be attractive for that. So our goal at that time was to go even lower, to use very, very quick sensor information about everything. So we had, as a challenge, we had only these distance sensors. So these are the distance sensors that are on that later robot that you barely see are better. Down here, this long thing is just a rubber tube around an emitter. So it emits infrared light. And then this little box is the receptor that measures the amount of reflected light. And there are 5 of those. They are, again, sequentially sampled. And then there are 2 sensors that are hard to see. It's actually, we literally use some Lego here. And here is a sensor. It's hard to see. That's actually just a light-dependent resistor with a lens that's sort of built into the sensor. And there are just 2 of them. And this was essentially to go to phototaxis, to go to light sources. And in the later work that actually first, and I didn't show you, the targets were sound sources, right? And sound sources makes much more sense than light sources. I'll come to that. But this was like cheaper and lower level. And so that would be the kind of a very low level sensor that the behavior-based guys really wanted. It's just a handful of cheap sensors, and then you define elementary behavior. So here it would be obstacle avoidance and target acquisition in the sense of light sources, and then have a very crude algorithm for that. We also had non-calibrated motors. That is, these motors were driven by little servo motors in which we actually disconnected the servo. We took a toy model, toy plane models that control the flaps, and we just cut off the sensor circuit, literally by cutting off the cable. And therefore, so they're motors that just take a voltage, and there will be a certain turning rate coming from their voltage, but it will not be calibrated. So if they run on carpet, then they will run more slowly than if they run on hardboard or whatever mechanical condition. So as a demonstration that we don't need this form of calibration and all that, because the planner itself makes an attractor, and the dynamic system, it's an attractor, that does the control. So if you don't turn it enough, well, then you get the sensor information that the obstacle hasn't been avoided, so you turn more. So without relying on a control system somewhere else. So these are here. These are just the batteries, 8 AA batteries, which were actually rechargeable. And this cable stuff is a little pin board there, how you connect these sensors to the digital processor. It was an integrated chip digital processor that the MIT would sell to universities, and now is in the Lego Mindstorm, commercially available, with a programming language, how you can program that chip. So it's I forgot the technical EEPROM, something where you can write onto the chip a code. It's called Interactive C, very low level language, where I think you had like 100 lines, something. Maybe, I don't remember the exact capacity. Maybe it's just somewhere. It's like a couple of 100 bytes or something like that. maybe it was 1.2 kilobytes or something. That's the memory of that chip. So, you know, that's what we call then really low level, right? It's a long time ago, you know, you can, every Coca-Cola machine has maybe better computers inside. Good. And so so one thing is you can't do that reckoning story there, you know, that would be way too advanced. So we cannot assume that we know where the target is. And so the only thing that we can know is where, if it's on the left or on the right, something like that. So what we said, okay, we can do this by changing the dynamical variable rather than doing the heading direction. That's the angular component of turning rate. We take the angular acceleration. So that's, we call it omega. So that's the turning rate itself, is the dynamical variable. So the dynamics will be the second derivative, you know, as a function of the first derivative. Because then you only need to know if you want to have a positive velocity or negative one, right? If it's on the left, you have a positive velocity for turning rate positive. If it's on the right, you want to have a negative velocity on that. And so we just choose two desired turning rates as attractors of a dynamics of turning rate, right? One derivative more. And then so that's actually already, I'll show you the equation. That's how we did the target acquisition. And then we had to translate the obstacle avoidance that is formulated in terms of heading direction, attractors for heading direction, into that thing. That's what I'll show you how we did that. And that sort of shows you attractor engineering. You know, that's why I do that. And you don't have to understand it fully, but you get the flavor of it. It's a very readable paper. I used to do an exercise about it. I'm not sure I'll do it. So let's look at obstacle avoidance. So this is for writing. I'll take you through the graphs and you can look it up. You know, we don't have to go through every sentence here. So we'll come back to that equation. So again, omega is the turning rate, right? With phi dot is omega. So omega dot is phi 2 dot. And there's this funny equation here. You're familiar with that if you did the dynamical systems tutorial. That would be the normal form of the pitchfork bifurcation, and you'll see the graph in a moment. This is just a constant written in some complicated form. So it doesn't depend on omega. Sorry, it's a constant relative to that, but you'll see it actually depends on other terms. So it's not quite the normal form of the pitchfork because there wouldn't be a constant here. It would be, without that constant, it would be the normal form of the pitchfork bifurcation. Okay, so here's some different dynamical regimes for that. So again, the turning rate is the dynamical variable. The rate of change of turning rate, so the derivative, the acceleration, the angular acceleration, the derivative of turning rate is here on top. And so this is an example where this is 0, and this will be a negative number. Then you have essentially, it would be a linear function. Now this makes a linear function with a negative slope, and this makes that it's a little bent, right? This term alone would make that you have here the slope is 0 here. That's what the third order polynomial is, right? And with this negative number, it just modifies this straight line this way. So this is means you have an attractor at 0 turning rate. So that's how you would program dynamically going straight. 0 turning rate as an attractor of the dynamics of turning rate. So that's what you want to do if there's no obstacle. Let's go. Of course, then you still have other contributions, as you say, if you want to go for the target. If you have an obstacle exactly in front of you, then you want to either go around it on the right or on the left, actually, flipped again. That means you want to have a turning attractor at positive turning rate or an attractor at negative turning rate, and there is a repeller at 0 turning rate. You, again, have to escape from that with some. Like if you suddenly run into an obstacle right ahead of you, you will go literally through a pitchfork bifurcation, which would turn that attractor into a repeller, and then there are 2 repellers turning it around on left. But it could be more likely, perhaps, that you run into an obstacle that's not exactly a midline, that's a little bit shifted. Oops, and then you might want to bias the bifurcation. It's not symmetric, not a pitchfork. As you want to say, I really oops, sorry, this is very sensitive touchpad here. I want to you see this way of flying. I want to have a larger range of attraction for this positive turning rate, which would be a positive turning rate would take you to the left. So that's when the obstacle would be on the right. And then I didn't plot the other one, right? If it's just the other way around, you shift that down so that the attractor here for turning to the left, which is decreasing, small, decreasing turning rate, negative turning rate, that becomes dominant, right? You shift it up or shift it down. And it's this term that will decide whether shift it up or shift it down. We'll understand in a moment how that works. So that's how you would break the symmetry. You make it more likely that you go around it on the right or go around it on the left, depending on where it shows up first. And this is just a more extreme form of that, where the alternative attractor is gone. It would be only relevant. Again, this is all happening because it's dynamic, right? You're maybe close to the attractor, but not exactly in the attractor, and therefore it could be that you're already in this attractor, and then this could be one moment when you still experience that. But if something on the right is really close, then you want to give up on that alternative solution and really force that it has to now make a turn to the left, so it goes to this attractor. And this is so it's just the individual. I already explained all that, and this is how we construct that additive constant, and that's based on the forcelet that you know very well, that you all analyzed, I hope, last week. Because we have the same sensors, right? Again, these are constant. Remember, this is constant, so very good for our code. They're just numbers that we have to put in there, and have the same logic here, right? And that creates this little thing, and that will mean every sensor will create that forcelet, and that forcelet informs us about what we should do. Namely, it tells us that here the obstacle is at smaller angles, which in the world means actually on the right, and here it's at larger angles. So the sign of that can be used to figure out if it's on the left or on the right. And the range of that, so where there is this forcelet versus none, tells us that there is an obstacle. So what we do here is we're flipping this around and making a function that measures whether there is anything. So we want to mark the region from here to here. That is a region where there is a forcelet. So there is a reason to avoid something. And so to do that, we make this into a potential. So we just integrate it. That gives us this function. Now, if you differentiate this, here you would have, it's actually minus, it's the gradient of this thing, right? So here it would positive slope translate into minus, and then here the slope is 0, that's the 0 crossing, and then here negative slope makes the plus here, right? So you can do that, you can integrate that. This is the result of that. That is this function here. And so we use that to have an indicator of whether there is an obstacle there. We make it a little sharper with this alpha. So that's a tangent arctan, but you could use others like sigmoid, so that we take the range where this is positive and make that positive. And then we actually also use the negative part of that to know that's where there's no obstacle. But it's, so the threshold for this is like the half width of that. That's how this here comes about. That 1/2 is pi half is this amount here. So we shift this whole thing up by that. If you do that, it's a real indicator function. So 0 and then something, right? But no, that's engineering. There are other ways to do that, but this is function engineering. And that's why I did these little exercises for you to work with functions, because in a lot of engineering tasks, that's what you have some desire, and then you have to write it down as a function. So it's like not the analysis of a function, but the design of a function, right? Inverse function analysis. So that you then can figure out the function and then also the parameter values for that. So we use this alpha here to control whether or not there is an obstacle. And so that's this term. And with this trick here, we can also, oops, sorry. So this defining term is really just that indicator function. So when this is 0, that means we're outside the range where there's a contribution of an obstacle. Then we turn that whole thing off. There's just a constant here. And this term is really just to have the sign to know if it's on the right or on the left, because this will tell us that, right? And so that whole thing is just this constant, while the rest is given by the normal form of the pitchfork. Yeah? If we go back, essentially, this here makes the normal form of the pitchfork. And by just shifting up or down, we create that bias term that comes from any obstacle. So, you know, the alpha here, that makes the pitchfork, right? That has to change sign. And that is this alpha, right? This is where you have an obstacle. This is where you don't. You don't have to look at these equations to understand it. So this is another way of looking at it. So if this is the force let, right? There's an obstacle right here in the middle. The force let, then I can say there are 4 regimes here. There is the center regime where I'm flying right there and I'm switching from no obstacle attractor to repeller. In this regime there, it would be symmetrical. And if I'm in this regime or in that regime, then I'm also doing that switch from here to a repeller, but I bias it in this way or I bias it in that way. And then outside here, I have no obstacle contribution, so I'm back to that same term. So there's a negative alpha and there's no shift up or down. And that's the summary of that. That turns out it works. Good. The target which motivated us to do that can be done in multiple ways. We did one particular way where we say the light-dependent resistor always votes for turning in that direction. So if I have one on the right, it tells me to turn left, so have a negative turning rate. No, it's a positive turning rate in mathematically, so turn to the left. And I take just some default value for that turning rate, like this one here. That would be my attractor for the light on the left. And on the right, I have the same symmetrical. I have an attractor on the right at the corresponding other turning rate. So if the two sensors get the same light intensity, then they sum to, I didn't even plot that case, but then they would sum to have a attractor at 0 turning, would go straight. And so if one of them receives a little bit more light, then these two attractors are shifted, and that will lead to the average, you know, moving to some turning rate that's on the left and right. So where the resulting attractor is a question of how different the light intensities on the left versus on the right are. And there's a gain factor, right? That's depending on how sensitive that is, that will determine how sensitive that is. So this is very much similar to those of you who've seen my other lecture where I do Breitenberg. This is a dynamical version of a Breitenberg vehicle. Maybe nobody here. I know one person who saw that, perhaps. Or not. Did I not teach that last semester? I did. No? Oh, in cognitive science, I did. But maybe there's nobody here from cognitive science. Anyway, it doesn't matter. It's just to make that connection. So that's very trivial, right? There's no bifurcation going on. This is like a control system. Yeah, and then we just add it all up, and the adding up really this is just mathematical information. There's nothing there. We just add these up. Yeah. So this is the implementation. Here's actually 32 kilobyte of RAM. A little bit more than I remember. It's good. Yeah, 8-bit. Probably it doesn't exist anymore right now. Yeah, that's this thing. We called it Rodinsky for some reason. Here, it worked. So here's an example of us recording. I'll show you a video in a moment. This is very much the thing you'll see in a moment. So it was able to navigate, so avoid obstacles and go to light sources. The downside of this is the actual video. The light sources have this drawback that it works pretty well in the dark. You know, vision is actually about reflection. All seeing with you have a hard time even saying whether I mentioned that in the introductory lecture. I think that vision is about surfaces and their reflectance properties, while audition is more about sources. You hear there's noise coming from this window, and you know there's my voice coming from here and so on. That's there's some echo as well, but it's a smaller contribution. That's why if you use the sensor to be about sources, auditory sensing makes more sense. But we build it as a demo. So here we always had to work with the windows closed because I must say we even had some sun. So we had to make sure that the windows are closed, so it doesn't always go for the windows. And then we control with these bulbs, we control some local sound source, light source. So I think you have a demo. This is Estella, by the way, who did that. Is this girl there? Avoids obstacles. Again, has no plan, right? It just follows the wall. It avoids her. And then at some point it so the differences in light here are weak. So now this is a strong light. We'll turn on this light. Little. So far it doesn't, of course, sense that at all. It's just this wall following, right? In the same way the other robot does that. So that shows the second order dynamics has the same properties as the first order dynamics with respect to that. Here you see now it does suddenly pick up that difference and goes there. We also controlled the speed. The higher the light intensity, the slower speed. That's why it stops. And therefore we could make it go to that other light source and stop. And this is really sometimes called phototaxis. And then it oscillates a little bit because now there's no source and finds its way out again. Kind of cool, right? And then it takes some time for, so far the sensors point in the wrong direction, but now one of the sensors really gets some input and well, isn't that cool? Yeah, that just, we used this at that competition where we had a lot of trouble with the light because there was lights in there, and there was actually a television team coming with their lights. And I don't know if it was, but it was doing very good obstacle avoid, so everyone was very impressed because ours didn't get stuck in corners. Yeah. So this was all a toy demo, and we did then have this drone project, but we only simulated the drones, and this person who works in Brazil has used this in the meantime to actually drive drones in some way. I don't know about the details of that one. Good, so this works, and so just a moment of reflection. So why does it work? What does it do? So this is now a system that is always in or near an attractor of turning rate, right? It's easy when the turning rate is 0, right? It's flying straight. But when it is turning, it is in an attractor for turning rate. And so as it is then actually turning, the bifurcation happens, right? So it's turning to avoid an obstacle, and then ultimately maybe to go around. And as it stops turning, it actually went through a bifurcation because now it's no longer in the obstacle range, right? And it's now in this range where it again has returned to the regular, to the attractor at 0, and that's how it goes straight. And when it goes around in the arena here, if it goes around that is really just the straight attractor. It's this kind of attractor that is modulated by the task, by the target, right? And so when it's driving around here, it's sitting in that attractor. So in other words, it's only when it does this obstacle avoidance kind of turning that it goes through a bifurcation where it suddenly has an attractor. It's on the left or on the right, and then it will only briefly during that flight, and then it goes through a bifurcation again. Right? Some of the more gradual stuff, like when it avoids things here, that is again just a very small, where is it? A small modulation, because what would happen here is that you have a little bit of a contribution, and this is a strong contribution, a little bit of contribution that lifts this up and down, so you can even have that is just wiggling, shifting the attractor a little bit by having a little contribution. But as long as the contribution is stronger, you go through that bifurcation, so you will actually really get that situation. So all the time the system's going through instabilities, right? But the attractors really determine the behavior where it is going. And this is something that one can use in all kinds of other contexts, for instance, in catching and so on. So this group in Lausanne that I mentioned, or the YAST team, does much more sophisticated stuff like that, where the system, and that involves actually also timing. So it's not just fixed point, but sort of limit cycle attractors. And there's just for one cycle, or sometimes in half cycle, that attractor there, and it's gone. But you can organize the solutions of the dynamic system by these attractors. That's it. Good. So that's all I have here on the subsymbolic. We're even a little early.